Okay, welcome back. Oh man, this class is basically kind of over. We have 2.5 weeks left, and what we're going to do now is we're going to start the last unit. What have we accomplished this whole semester? We posed the two problems of calculus, the tangent line problem and the area problem. We did a whole unit for a month on limits, learning how to deal with infinitely small and infinitely large quantities. We solved the tangent line problem by inventing differentiation. We learned how to differentiate every single function. We applied differentiation via the mean value theorem to learn all kinds of things about when functions are increasing, decreasing, concave up, concave down. We solved related rates problems and optimization problems, and extended differentiation to parametric curves and to implicitly defined relations between variables. And that was amazing. Then we returned, we solved the area problem by inventing integration, and we explored all the different techniques that are available to find the integral of a function, and we proved integral properties, and it culminated last week with the fundamental theorem of calculus, which shows that differentiation and integration are inverse processes. And this week we have been continuing to explore and strengthen our understanding of that relationship. But now we're done. And now, what comes next, logically speaking, applications of integration. We have defined integration, or maybe I should say, we were inspired by integration. We were inspired to invent integration by considering the problem of some velocity versus time curve, which was, say, positive, and we convinced ourselves that the area under this curve would be the distance traveled. That's what started us finding the areas under curves to begin with, plus just curiosity to see if we could do it. We then solved the problem of how to integrate stuff, basically. And then we've already started, I suppose, using this new power of integration to do things. One of the things that we can do is stuff like this. We can, if we have a velocity versus time curve, we can find the distance traveled. But you have already seen that integration is far more broad than that. Because if, for example, this is not a velocity function, but say, I don't know, the rate at which gravel is arriving at some gravel processing plant, well then, the integral from time A to time B will be the total amount of gravel arrived. So that's the more general notion that the integral represents the net change. But we have seen even two more examples in which things that didn't seem to have anything to do with the area under the curve at all were still subject to integration. One of those was the average value of a function on a certain interval. So you had some function and you wanted to know how big it was on average. And I stressed, I hope, in this video multiple times, I think, in multiple videos, that if I want to know how big this function is on average, this doesn't really have anything to do with the area under the curve at all. And if you were to, and what do? We sample this function sort of infinitely often, and we sum up all these y values, and then we take the sum of all those y values, and we divide by how many y values there are, and then there's this sort of extra b minus a lurking on the sides that we multiply by, and then this turns into an integral. And so here you might ask, what does this have to do with finding the area under a curve? This is the formula we came up with for average value, and the answer is it doesn't necessarily have anything to do with finding the area under a curve, which shows that integration is a more general process than just finding the area under a curve. Integration is the process of adding up an infinite number of infinitely small things. And here the number of infinite things we're adding up are the y values. I think I've said all this already multiple times. What was the other big thing that we did that didn't have anything to do with the area under a curve at all? It was volume. And that was kind of a preview, something I've never done before, of this unit. In a previous video from last week, we found the volume of a cone by splitting it up into an infinite number of little disks. Okay, what's the big picture here? The big picture is that this unit on applications of integration requires you to have a sort of deeper and broader understanding of integration. Integration is the process of adding up an infinite number of infinitely small things. And any problem that you want to solve that involves adding up an infinite number of infinitely small things, integration can do that for you. That may be area, that may be volume, that may be the length of an arc you can think of as the sum of an infinite number of infinitely short line segments. The surface area of some curve could be represented as a sum of an infinite number of little strips. You can find the total work done by some sort of moving object in physics by adding up an infinite number of infinitely small bits of work. Okay, so all of that is coming, and we are on chapter 7 now, applications of integration, and we're going to do a little bit of this now, and then this is the first thing that you do next year. Okay, this was kind of an intro to the last 3 weeks of this class. What we're going to basically do in Analysis 1A for the rest of this year, and then you're going to pick it up next semester, is geometric applications of integration. And the main thing we're going to do next week is volume. But this week, we're going to do perhaps the most boring application of integration of all, which is the area between two curves. And area between two curves. I say this is boring because in some ways it is not new at all. And in fact, everything I'm about to teach you is kind of like not really new. But it is new because it's not new, but there are sort of techniques that can help you do this. And there's a different way of sort of thinking about what's going on. All right, there's a worksheet. This worksheet is called Area Between Two Curves. It's just a single piece of paper, front and a back, with 5 problems on it. We're going to do those 5 problems right now together, and then that's that. The homework on this is, I think, hard, but not in like a deep theoretical way that involves a lot of intense thinking. It's just like the problems are hard. So this lesson is going to be quite short, but the homework for this might take a while. Okay, or maybe I just won't assign them any problems. Let's go! The very first problem says, find the area of the region between, this is number 1, between y equals secant squared and y equals sine x from x equals 0 to x equals pi over 4. Okay, and alright, the probably hardest part, or what can be a hard part of doing these problems is just the fact that you have to read and interpret and understand and think and draw the pictures and understand the situation that's going on. So I think there's a lot of care that goes into setting it up. So we need a graph. We need a good graph. And okay, what does secant squared look like? Alright, well, personally, I just know, because I just know things, that secant squared starts and looks like this, and then these like asymptotes. So what happens if you square secant? Well, if you square secant on the interval from negative pi over 2 to pi over 2, it just kind of like stretches out like, even more. Okay, so anyone who is very experienced in pre-calculus should be able to make a good, accurate graph of secant. And here is what it kind of looks like. If you plug in secant squared, if you plug in 0, secant of 0 is 1. So we're up here at like 1. And if you plug in pi over 4, see, cosine of pi over 4 is root 2 over 2. So 1 over that is just root 2. And therefore, secant squared of pi over 4 is 2. So here's pi over 4, and up here is 2. Boom. And so secant squared kind of looks like that. And I shall now label this y equals secant squared x. Okay, that wasn't too hard. Next, what does sine look like? Well, sine's just kind of doing its thing. It's going to peak over here at pi over 2 comma 1. So at pi over 4, we know that it's root 2 over 2, which is about 0.7. So, I don't know, something like that. Whatever. Okay, that's root 2 over 2. Good. And this is y equals sine x. Okay, and now we realize, now that we've graphed these two functions, what the actual region is that we are trying to find the area of. It's the region between x equals 0 and x equals pi over 4, enclosed by these two curves. So I will now shade this region green. So there it is. Okay, so I need to find the area of this green region. Now, you're probably thinking, dude, don't I already know how to do this? And the answer is, yeah, you do. How would you probably do this problem? Any normal person in this class would say, oh, okay, well, I know if I take the integral of secant squared, then that will give me the area under the secant squared function. And now I just subtract out from that the area underneath sine, and that will give me the green area. That is absolutely correct and fine. But I would like to encourage you to sort of think about this all a little bit more abstractly. And instead of thinking of us as taking one big area and subtracting some other area out, let's just sort of directly compute the green area. And how shall we directly compute the green area? Well, by splitting it up into an infinite number of infinitely small things. And in this case, those infinitely small things are going to be these little strips. So I have these little purple rectangles, and what are these little purple rectangles? Well, they're rectangles whose bottoms are determined by the height of the sine function, and whose tops are determined by the height of the secant square function. In other words, what I'm really doing is partitioning the interval up into subintervals. I'm going to the ith subinterval, I'm picking a point, x sub I star, and I'm plugging that point x sub I star into these two functions. And what I get is okay, it's getting a little messy, so I don't want to draw this, but what I have now is a rectangle, and the width of that, like this, the width of that rectangle is delta x, and the height of that rectangle is, well, it's the difference in the heights of what happens when I plug x sub I star into secant squared, and what happens when I plug x sub I star into sine. Okay. And if you think about it this way, then what we are really doing is we're taking the sum from I equals 1 to n of a bunch of things. What are those things that I am summing? I'm summing up rectangles. And those rectangles have dimensions, like I just said, secant squared x sub I star minus sine of x sub I star, and all of that is being multiplied by delta x. And that will give an approximation to the true area under the curve. And if I then take the limit as n approaches infinity, then this will give me the exact area of this green region. Okay, of course, what does this turn into? By the definition of the integral, this is just going to be the integral from 0 to pi over 4 of secant squared x minus sine x dx. And of course, this is exactly what I got the other way, but here somehow I've understand it better. I'm conceiving of this green region as being one sort of thing which gets partitioned up via these rectangles. Okay, if you're unconvinced that this is all necessary, that's fine. Hold off for one more problem. Anyway, at this point, let's just do it and get an answer. Well, fundamental theorem of calculus to the rescue. Do you know how to antidifferentiate secant squared? I do. It is tan. And do you know how to differentiate negative sine? Yeah, it's cosine. So I guess we just get tan plus cosine, right? Secant squared minus sine. Yep. Evaluated at pi over 4 and 0. Now we have to sort of be careful. Tan of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. That's a plus. And then minus tan of 0 is 0, but cosine of 0 is 1. Yeah, that's just true, plus 1. And so the overall answer is just root 2 over 2. Is that answer reasonable? Yeah, I guess so, because actually it doesn't look very reasonable. I don't know. Sure. Yeah, because this whole thing is kind of a, well, I don't know why that's actually reasonable, but I suppose it is This graph is sort of not to scale, but if this is root 2 over 2 and 1 is out here somewhere, it's not totally crazy that this green thing would have the same area as this red thing, so that's plausible. Anyway, the math checks out. This is the right answer. Okay, good. That was maybe totally boring because we just knew everything. So let's do something that's a little bit harder. Harder problem. Find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. I'm on number 2 now. Okay, so before I can even sort of begin to do this problem, I need to figure out what the region is that I'm trying to find the area of. And this region has been described geometrically as the area enclosed by 2 curves. So all the effort sort of comes, I think, in this stage right now, where we try to make a picture of this situation. And okay, it's really sad for us to be doing this remotely because this is one of these classes where I say almost nothing and I just have everyone just working on these problems and everyone's looking at each other's paper and talking it out and you're basically figuring these out for yourself. So you should do that right now, but okay, pause and try it or not. What does this look like? Well, I need to do a couple things. I need to graph these things. So okay, so if I try to do that, what do I get? Let's see. So, let's try to make an accurate picture. Well, y equals negative x, of course, looks like this. And what does 2 minus x squared look like? Well, it looks like this. That's 1 and that's 2. It's going to be an upside down parabola which has been moved up 2 and it will cross the x-axis at like, negative root 2 and root 2. So like, 1.4 or whatever. And it's going to be a parabola and it's going to be like that. Okay, so with not too much effort, I have determined that really this problem was all about finding this area, the area inside this parabola and this line. Okay, and this problem is sort of unambiguous because it is just true that these 2 curves define a particular finite closed region. But as opposed to the previous problem, where I was sort of just given, I was told sort of where to start integrating and where to stop, or I was given the sort of horizontal bounds of my region, here I am not given that information because I have to sort of do that myself. Okay, so I think you all see that the very next step here is to find the points of intersection. So let's just do that. Perhaps I can just squeeze it right up here. When does 2 minus x squared equal negative x? I'm solving for the points of intersection. Well, I'm just solving for the points of intersection. So okay, this just becomes x squared minus x minus 2. And I think this is just a simple quadratic equation. So I get x minus 2x plus 1. And so, according to my math, these 2 curves intersect at 2 and negative 1. And that's starting to look pretty good. When x is negative 1, of course, that point is that's negative 1 comma 1. And here my picture was a little bit crappy, I now see, because in fact, when x is 2, y is negative 2, and so really we should have had like a negative 2 here. So yeah, my parabola maybe was a little bit inaccurate. It's going to be kind of more, flaring out or something. Anyway, now this is starting to look good. Okay, good. Having done all that sort of preparatory sketch work, I now see that it is this green area that I am this green region that I am trying to find the area of. And actually, if you remember from the very first day of Analysis 1A, we talked about how Archimedes' kind of like crowning achievement was to be able to find the area of a so-called parabolic segment, which is the region enclosed by a parabola and an intersecting line. And so we're about to do that problem that for Archimedes required an extremely convoluted argument that only like a genius could make, involving like an infinite sequence of triangles constructed with tangent lines and all this kind of stuff. But whew, with the fundamental theorem of calculus, this is just a piece of cake. Okay, good. How are we going to find this area? Well, perhaps now you see what I was rambling about in the previous problem. It would be sort of, not impossible, but it would be sort of awkward to find the area under the 2 minus x squared curve. Because what does that even mean anymore, right? Once this function starts becoming negative, then I don't even know what the area under that curve means. It's not actually giving me the right answer anymore. And the area under the y equals negative x curve is also like not right. So it's for these kinds of reasons, it's best to sort of abandon that approach of thinking of this as two separate problems, and really just think of this region as one coherent region. And what do we do with this region? We split the partition, the interval, from -1 to 2 up into subintervals. And now we pick an arbitrary, we go to the ith subinterval, and we pick a sample point. And then we construct the height of one of these, I call them representative rectangles. In other words, we think of this green region as a single shape, and we find the area of this shape by dividing it up into an infinite number of rectangles. And what are all those rectangles? What do they all have in common? Well, what they all have in common is their height is simply the difference in the y-coordinates of the parabola and the line. And here's where I think this is really nice, because this is 2 minus x sub I star squared. Hope this is all clear. Minus negative x sub I star. In other words, regardless, notice that the parabola is sometimes positive and sometimes negative. Notice that the line, y equals negative x, is sometimes positive and sometimes negative. But it's just always the case for this entire interval from -1 to 2. It's just always true, starting at -1 and ending at 2, that there's a rectangle, and the rectangle's height is just the top y value minus the bottom y value. In other words, for any x value, if I plug it into the parabola, get a certain number, it might be positive or it might be negative. For example, over here, I'll have a sort of different rectangle, but it's still true that the height of that rectangle is just the difference in the y-coordinates. So you don't need to sort of think and stress about positives and negatives if you think about it this way. Okay, enough rambling, we do the problem. What is the problem? Well, we are going to sum up from I equals 1 to n a bunch of things. What things? Rectangles. What are those, what are the dimensions of those rectangles? Well, the height of the rectangle is 2 minus x sub I star squared, and the minus minus negative x sub I star, and the width is delta x. In other words, yeah, I think you get it. And if I take the limit as n approaches infinity, then that will give me the exact area of this green region. Okay, in other words, I think it is worth it a couple times. I know this gets sort of annoying because no one wants to think about Riemann sums, but it actually makes you sort of smarter and understand things better if you first represent things as a Riemann sum. I might skip it from now on. Okay, and of course this turns into an integral. The integral from -1 to 2 of 2 minus x squared plus x dx by the definition of integral. And so now, if I can just do this integral, then I can find this area. Alright, and this integral is like, this is easy, but you still, if you're going to do this by hand accurately, you do need to kind of be careful. So let's go. Here you get negative x cubed over 3 is the antiderivative of negative x squared plus 2x. Plus x squared over 2, and then plus 2x. This is me just sort of rewriting this in normal order. Okay, great. And now let's do it. If I plug in 2, I get negative 8/3 plus 2 plus 4 minus, you gotta use a lot of parentheses if you're gonna get this right, plug in negative 1 and that gives you negative 1/3, but then so like plus 1/3 plus 1/2 minus 2. I think I did that all right. And so that gives me minus 8/3 minus 1/3 is minus 9/3, so it's minus 3. And then that's plus 6. And then that's minus 1/2 and then plus 2. So I in fact get 5 minus 1/2. And so I hope the answer is 4.5. Ta-da! Okay. Good. There's about 2 more things, sort of worth doing. So let's just immediately go to the next problem. Okay, next problem. Yeah, here we go. Number 3. It says, find the area of the region enclosed by the graphs of y equals 2 cosine x and y equals x squared minus 1. Okay, so far, this does not appear to be any different from any of the other problems we've done. In fact, I'll just go and graph this right now. Here's 2, and this is cosine, so okay, what do we have here? X squared minus 1, so that's going to intersect here and here. So we have, that's x squared minus 1, and cosine, if that's 1, I guess it will cross that pi over 2, which is, 1.5 or so. So if that's 2, here's going to be my, la, and we got something that looks like that. Okay, so great. This is y equals 2 cosine x up here. This is y equals x squared minus 1 here. Those two curves define a certain region, and that region is this one. And now I just need to find the area of that region. So far so good. This doesn't appear to be any different from any of the previous problems until you go to try to do it. You suddenly realize, like, okay, I need to partition, blah, 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 but like, I can't sort of proceed with this problem until I know what these points are. And unlike the previous problem, I can't simply set 2 cosine x equal to x squared minus 1 and hope to solve that. I just can't solve that, right? There exists no sort of algebraic closed form expression which will give me the solution to this sort of transcendental function and this algebraic function. So I have to do something more fancy, and in this case we're just give up and use technology. Okay, so this is an example of a problem where we're just going to use our calculator because we can't do the integral. But what is the integral that we need to do? Well, first of all, I noticed that both of these functions are even. So in fact, the sort of smooth thing to do now is to only calculate half of it and then just multiply by 2. And so I'm going to partition the interval from 0 to, I still don't know what that point is yet, up into subintervals, and I choose a sample point from the ith subinterval, and I get a rectangle and I add it all up. But okay, I think people are getting sick of this, and I am too, so this time I'll just go straight to the integral. But I'm still thinking of myself as partitioning and constructing rectangles, but I'm now going to add up those infinite number of rectangles, and that's really what an integral is. It's an infinite sum. And what am I summing? I'm summing a bunch of rectangles whose heights are 2 cosine x minus x squared minus 1, and whose widths are delta x, the infinitely thin width of one of those subintervals. 2 cosine x minus x squared minus 1. And I'm going to do it from 0 to, okay, this is what I need to figure out, and then I'm going to multiply by 2 because I'm saving some work by observing that this function's even. Okay, so now, man, this is annoying again, but we do it. Oh yes, high tech. I promise that one day I will not be doing it this way, but today is what I'm doing. Okay, so what do? We go to Geogebra, geogebra.org. You go here, you click on graphing calculator, and we now just begin, man. What am I going to do? First I want cosine, let's call that f, is 2 cosine x, boom. G is, I'll do this fast now, G is x squared minus 1. Confirm that things are all looking like as we want them to, and notice if you're not too particular about your window, you can just sort of drag and zoom, and all that stuff's kind of like nice. Whew, it's 2020. Computers, technology. Okay, so we want to find this area. So first I need to find that point of intersection. That was the whole hard part, right? So we go once again to the Geometry Tools tab. We click Intersect. Maybe this is the better way to do it. Click these two curves. Boom. It will construct the intersection of those two curves. Go back to the calculator screen. Note that it's named that point A. This is all so wonderful. 2 times, and now I want the integral from, or of what? I want the integral of f minus g. And so you just type f minus g. This is so beautiful. Okay, that was a big nightmare. What the hell happened? Okay, 2 times the integral of f minus g. Yeah, you just hit the right cursor, I guess, not tab. Yeah, starting at 0 and ending at the x coordinate of a, which is x of a. And enter. Boom. There you go. It is not, for some reason, oh, it doesn't shade because I guess that 2 makes it sad or something. No, it's still not shading. I don't know. It just didn't shade. Okay, I liked the pretty picture, but never mind. Here we go, and the answer is 4.9949, blah, blah, blah. So it's very, very nearly 5, but not quite. I would report that answer as 4.995. Or you could say 5.000, but it's not quite 5. Okay, good. That problem is done, and we will now do another problem. Flip to the back of the worksheet, and okay. And you can just, while I get this all set up, you can just, in class I would give everyone like 4 minutes to like, you know, do it all themselves first. Far more satisfying, but